In this video I'm going to be talking about Olber's paradox, and he actually looked at Newton's model of the universe. And now Newton basically stated that the universe was infinite, so it was infinite in extent. There was an infinite number of stars, infinite both in the size and in the number of stars. He also said it was static and it was eternal. So that was Newton's view of the universe. Newton's view. Now, Olber, who was an astronomer, when he looked at it, he saw that there was a paradox. Now, in simple terms, if there was stars everywhere in the universe and they were infinite in number and in every single direction, then what Olber basically said was that at every point in the night sky there should be a star, and so the night sky should be bright. Instead it's dark, so there's a paradox there. Now you can also view it from a mathematical point of view, and I like to use this diagram that I've sort of set up here to explain it. Now imagine this is the Earth over here, and we're looking out at the night sky, and I'm going to draw dots here. These would be, if this was a section of the night sky, I'm not going to do them all, there would be stars all the way around, and in Newton's view of the universe these would be reasonably evenly scattered about, and they would be everywhere. So we're just taking a section of the night sky. Imagine this as like a soccer ball, where this bit over here is like the leather of the soccer ball, so you've got a thin layer. Now the volume of this, we could write it as if this is the distance r here, and if this distance here is relatively small, we call x, then the volume of this, if we took this section here, the volume would be 4 pi r squared times x. And that volume would give us an indication of the number of stars. So the number of stars, and therefore the luminosity, would be proportional to the volume, because the greater the volume, obviously the greater number of stars, and that is proportional to r squared. Now we also have that the apparent brightness is equal to the luminosity over 4 pi d squared. In this case we are, instead of using d, we're using r, so r squared. So the brightness is inversely proportional to r squared. Now when we combine these two here, when we combine the two here, the luminosity or the brightness, this luminosity over here is proportional to r squared, and here we get inversely proportional to r squared. We can basically see that the apparent brightness is proportional to both r squared and inversely proportional, so it actually cancels each other out. So if I take any section, we would have basically the same luminosity coming out from it. So let's, for instance, if I took, let me cancel this, if I took another slither and I took another section, let's say further out, well, I won't go too far out, and we went out like that, so we have a similar, basically we would have that this new section here, let me do it, this new section all the way around over here, would give the same brightness as this section over here, because as we are going further out, the number of stars is increasing by r squared proportion, but also the brightness is decreasing because we're going a further distance out. So we would basically have, therefore, that as you went further and further out, you'd just be adding on more and more light. And because it's infinite in extent, it should be that the night sky would be bright. Okay, so I hope that explains it. If you need further explanation on that, I know it's not too easy to always explain and understand that, please come and see me and talk to me about it. Thanks very much.